Hello, Assalamualaikum and good afternoon. I'm Dr. Shaiman. I'm also an instructor of BE3143 Power System Analysis. So until now, we have covered all the parts of power flow analysis that contains Gauss-Seidel, Neutral-Raphson, and also fast decoupled. So start from this moment in this video, we are going to proceed to the next chapter, which is called as balanced fault analysis. So we are going to start with the circuit reduction and Thevenin technique. Okay, a fault in a circuit is any failure which interferes with normal flow currents. So the keywords here is failure. Okay, failure. Right. Examples of fault in the circuit, basically overload. Okay, overload is the normal term that we use. Overload in distribution system network, faults on electrical equipment, transmission line fault. So it can come from the electrical appliances or equipment or transmission lines, right? So overload faults are caused by the unexpected increasing of loads. So faults on electrical equipment are caused by this is very common to see, which comes from the lightning. This kind of lightning usually it's very unexpected. It's totally due to the weather condition, and the lightning happens. Okay, when the lightning happens, it's totally break the system and trigger your MCB or ESCB system to be blackout. Okay. Then another thing is the transmission and distribution overhead lines. Overhead lines is the transmission lines pole that you can see in the side on the side of the roadways or the highways. Okay. Which is basically caused by the lightning, storm, fallen trees, and the one is snow, snow or icing. But we cannot experience it in our country because we're not in a fossil country. Alright, this is an example of picture I just pick up from the internet. Please don't claim anything from me, just for educational purpose, for making you understand well. So this happened, you can see the edges of the buildings. The stones, the concrete here is fall into several parts. Okay, same like this. So the edges are struck by the lightning. Okay, there's two similarity here. There's similarity here between these two pictures where the lightning struck at the edge of the building or structure. Okay, you can just Google, or maybe you learn from other subjects. So why the lightning tend to strike at the edge of the system? Of course, we're not covered in this chapter, in this subject, but just for your basic understanding, your general knowledge, so you can Google it. What is the relation between magnetic field, and electric charges to the lightning occurrence? Okay, this is an example also. The distribution board, or we call that as DB. And DB, I think, experienced several explosion, maybe minor explosion. Maybe because of sometimes if the cable are not tightened up very well, so it can also create spark, which is finally led to the explosion. Okay, it was small explosion. Okay, here I am sorry to say to all the cows here, they are electrocuted and that because electrical fans. Basically maybe this is not the electrical fans, but due to some irregular or unstable or unreliable grounding system, which leads, because it's the steel, so which leads to the electrocution of the fans. And when by unluck, when the cows get near to the fans, so they are shocked and dead. Okay. So the example of electrical pole, again from internet, so just pick up from the internet. This one also transmission lines, the overhead lines is falling down, and this is something that we cannot see in our country. You can see that there's a snow here. Okay, snow here. The kind of snow, they are heavy. Okay, they are heavy, and which leads to the fault also. Okay, right. Okay. Analysis types. Basically in this subject, we are going to cover only two. So we have finished this part. Okay, this part we already finished. Power flow. Okay, evaluate normal operating conditions. I'm sure you still remember that. The Y bus emitters, the power flow analysis, the power flow diagram, the Neutral-Raphson, the Gauss-Seidel, and fast decoupled. Okay, so next from here, from now, we're going to learn the next, which is the fault analysis. So fault analysis evaluate abnormal operating condition, even from the term itself, because this is fault. Fault mean something wrong. Okay, something wrong about that. So that's called abnormal lah. Okay. Then fault types will be separated into two parts, which is in this video we are going to cover the balance fault, which contains about the three-phase fault, and another chapter. This is chapter 4. Okay, this is chapter 4. Sorry for my bad handwriting. Okay, we're going to cover single line to ground, double line to ground, and line to line. Right? Okay. Okay, why the result for analysis is very crucial? Right? Basically, it is used for specifying ratings of circuit breakers and fuses. Okay. Of course, there's some calculation sometimes, maybe at the end of this chapter, so you cannot still brain why is the relation between the circuit breakers. Actually, what we have learned, what we are going to learn now, is just apart from that. Basically, at the end, when the power system engineer, the real work of the power system engineer based on the power system analysis study, or fault analysis, so finally they want to specifying ratings of circuit breaker and CB, circuit breaker, okay, and also the fuses, okay. The ratings, how many amps, what is the most suitable for the system, okay, and also used for the protective relay settings to set the most suitable and reliable protective relay range, and specifying the impedance of transformers and generators. So we're going to play with the transformers and generator after this. I mean the specification of them, okay, right. This is what the fault analysis is used for, right. So magnitude of fault current depends on the fault currents is totally depend on the impedance of the network. You can say the line impedance, right? And then the internal impedances of the generator. Generator also, in the generator they also have the internal impedance itself, okay? Internal, okay? Right, next, the resistance of the fault. So we have the fault resistance or the fault impedance, okay? So network impedance are governed. So network impedance governed by the transmission line impedance. Okay, network impedance. We go detail for network impedance, transmission line, transformer connections, and grounding connections and resistance. So this is the network impedance are governed, right? Then I'm sorry for the until the slide. I choose to just read and some underline so that you can understand. For me, it's not the crucial here, but the crucial is about the calculation. After that, we are going to learn it, inshallah. Okay. So the generator behavior is divided into 3 periods. So this is the behavior of the generator. The first subtransient period. This part is the subtransient period, which is not stable yet. Okay. Very abrupt change. Okay. Subtransient period lasting for the first few cycles. And then the transient period is the period, this period, okay? This period is the font is very small, so I write with my bad handwriting. Right, transient period covering a relatively longer time. And finally, we're going to the steady state period. So this is the steady state period. So this is the part, okay, the part, steady state period, right? All right. So the subtransient period, SD equal SD, determine the interrupting capacity of HV circuit breakers to determine the operation timing of the protective relay, okay. And then for transient period is the stable state one, okay, to determine the interrupting capacity of MV. MV is medium voltage. This one is high voltage, okay, it's high. So means that subtransient, which is closely going stable but not stable yet, so that region is about interrupting capacity of HV, high voltage circuit breakers. So while the transient period is covered about the medium voltage, okay. So next, determine the operation timing of the protective relay for medium voltage networks. It's all about voltage, medium voltage, and then the transient stability studies. This study is totally we're not going to touch here because it's quite complicated and detailed study. Several PhD and masters are graduated from this topic, okay. So I'm not going to cover that, okay, right. it's enough for you just to know the very brief introduction of about the transition period and subtransition periods of the fault study, right? Okay. Fault representation, a fault represents a structural network change equivalent to the addition of an impedance at the place of the fault. An addition of an impedance. An addition to the addition of an impedance at the place of the fault. So if the fault impedance is 0, the fault is referred as a bolted fault or solid fault. Okay. This case, basically we are going to have some impedance, fault impedance we call it ZF. But for this case also, so we are going to learn 2 cases. The first case is ZF equals certain value. Second one is where the ZF equals 0, which is the fault impedance is 0. Okay. So first order method, the faulted network can be solved conveniently by Thevenin method. First order method, Thevenin method. Okay. Network resistance are neglected. So network resistance are neglected. Generators are modeled as an EMF behind the subtransition or transition reactance. So reactance here. Inertial capacitance are neglected and system is considered as having no load. So a lot of things as there's 2 things here are neglected. One is shunt capacitance neglected, and one is network resistance are neglected. Okay, all right. So this type of fault is defined as the simultaneous short circuit across all 3 phases. Okay, that's why we call that 3-phase fault. Okay, 3-phase fault occurs not so frequently, but is the most severe type of fault encountered. Okay, so occur not so frequently, but it's the most severe type of fault. So this is the example of balanced 3-phase fault, and this is the balanced 3-phase fault to the ground. Okay, just the basic idea. Don't worry. If you still cannot understand here, it's okay. We just proceed to the next, right? Don't worry. Okay, now we start with the first equation. Okay, all right. Short circuit capacity, SCMVA, right? Also known as short circuit MVA. In the question, basically, I'm going to say short circuit MVA. Okay. It's a common measure of the strength of a bus. So it's used to determine the dimension of the bus, interrupting capacity of circuit breaker. But what is the most important here is the equation. Okay, this equation. So this equation, short circuit MVA equal to root 3 VL. Okay, VL and then I have fault current. Okay, so this is the line voltage, then multiply with 10 to minus 6. Okay, so the symmetrical 3-phase fault current is given by this equation. So where V0, so here V0 is pre-fault bus voltage, and ZPU is a subtransition impedance. So there's a calculation how to calculate the ZPU. Okay, but don't panic, we are going to look at this as the example, right? Okay,